And now let's discuss another important theorem on continuous functions. And as per this theorem, the exponential function a to the power x, where a is greater than 0, is everywhere continuous. Now here we have to prove whether the function f of x, where f of x is equal to a to the power x, is everywhere continuous where a is greater than 0. And now as per the definition of continuity, a function is continuous at any point if and only the limit of the function at that point is equal to the value of the function at that point. So let's first of all check the continuity of this function at the point x equal to 0, and it will be continuous at x equal to 0 if and only the limit x approaches 0, f of x is equal to f of 0. So let's first calculate its limits. Now limit x approaches 0, a to the power x. Now in order to calculate this limit, we can also write a to the power x as a to the power x minus 1 plus 1. And again a to the power x minus 1 plus 1 can be also written as a to the power x minus 1 upon x into x plus 1. So now this limit becomes limit x approaches 0, a to the power x minus 1 upon x into x plus 1, and which can be written as limit x approaches 0, a to the power x minus 1 upon x into limit x approaches 0 x plus limit x approaches 0 of 1. And why is it so? Because the limit of product of two function is equal to the product of their limits, and similarly the limit of sum of two functions is equal to the sum of their individual limit. And as per the definition of limits, limit x approaches 0, a to the power x minus 1 upon x is equal to log of a to the base e. And when x approaches 0, then x will be also a very small number close to 0. So this limit becomes log of a into a very small number 0, or we can say it will be also equal to 0 plus 1, and which is equal to 0 plus 1. So the limit x approaches 0, a to the power x is equal to 1. And what's the value of the function at the point x equal to 1? Or f of 0 is equal to a to the power 0, and a to the power 0 is equal to 1. So that means the limit of the given function and the value of the given function at the point x equal to 0 are both equal. And that means the given function a to the power x is continuous at x equal to 0. Now let's check the continuity of the given function at any other point c, where c belongs to real numbers. And for that, let's calculate its left hand limit and the right hand limit at x equal to c. Now its left hand limit, limit x approaches c from the left hand side, f of x can be also written as limit h approaches 0, f of c minus h. Why? Because if we write x as equal to c minus h, then when x approaches c, then in that case h will also approach to 0. So, and what's the value of f of c minus h? F of c minus h is equal to a to the power c minus h. So this limit now becomes limit h approaches 0, a to the power c minus h, and which is equal to a to the power c into limit h approaches 0, a to the power minus h, and which is equal to a to the power c into limit h approaches 0, 1 upon a to the power h. And now when h approaches 0, then a to the power 0 is equal to 1. So this equation finally simplifies to a to the power c into 1 upon 1, and which is equal to a to the power c. And what's the value of the given function at the point c? And it is also equal to a to the power c. That means the left hand limit is equal to a to the power c, and which is equal to the value of the function at the point c, or f of c. And now let's calculate its right hand limit. Now limit x approaches c from the right hand side, f of x can be also written as limit h approaches 0, f of c plus h, and which is equal to limit h approaches 0, a to power c plus h. Now as per the properties of indices, a to power c plus h is equal to a to power c into a to power h. So this limit now becomes a to power c into limit h approaches 0, a to the power h. And when h approaches 0, then a to power h will be a to power 0 or 1. So now this limit becomes a to power c into 1, and which is equal to a to power c, and which is also equal to f of c. So that means the right hand limit is also equal to the value of the function at the point c, or f of c. That means the right hand limit at point c is also equal to the value of the function at the point c, or f of c. So here the left hand limit and the right hand limit and the value of the function at the point c are all equal. So that means the given function is also continuous at the point x equal to c, where c is any real number. So we have already proved that the given function a to power x is continuous at x equal to 0, and it is also continuous for any arbitrary point c, where c belongs to a real number. So that means the given function f of x defined by f of x is equal to a to power x is everywhere continuous function. Now let's solve some questions based upon this theorem. And the first question is, prove that the function f given by f of x is equal to 2 to the power x plus sin x is a continuous function. Now here the function f of x is given by 2 to the power x plus sin x, or we can say that the function f of x is sum of two functions 2 to power x and sin x. Now if we can prove that 2 to power x and sin x are both continuous function, then that will also prove that f of x is also a continuous function, because the sum of two continuous function is also a continuous function. And now let's first check whether 2 to power x is a continuous function or not. And in the theorem which we just learned in this episode, the exponential function a to the power x, where a is greater than 0, is everywhere continuous function. And in 2 to the power x, a is equal to 2 and 2 is greater than 0. And that means the function 2 to the power x is a continuous function. and the second function is sin of x. And this function 2 we have already learned in previous episodes that the function sin x is also a continuous function. So now the function f of x is a sum of two continuous functions, and as per the properties of continuous function, the sum of two continuous functions is also a continuous function. So that means the function f of x given by 2 to the power x plus sin x is a continuous function.